Okay, let's get started. Okay, so today we're going to learn about concurrency. Specifically, we're going to learn about processes, which you should have already seen before, threads, which you should have already seen before, and address spaces. And we're going to start to talk about some of the issues that we have when we have concurrency in systems. Okay, so let's start with a very brief history of operating systems. Okay, so there were several distinct phases that operating systems went through, and this was really reflective of the cost structure of systems. So originally we start out with mainframes. They're incredibly expensive, tens of millions of dollars, and relatively speaking, people are cheap. Okay, so these are systems like ENIAC, System 360, System 370, and operating systems like Multics. All right. Next phase, hardware becomes a lot cheaper. So now we're talking about mini computers that cost hundreds of thousands of dollars to millions of dollars, so at least an order of magnitude cheaper. And humans now are expensive because you're paying humans tens of thousands of dollars a year in salary. And when we take this to the extreme, we get to PCs and workstations, where now you're talking about computers that cost a couple $1,000s to maybe $10,000, $20,000, and you're paying people tens of thousands of dollars. So the equation is now flipped, and people are much more expensive. The hardware is much cheaper. All right, so now it becomes important to make the computers more usable. Up until this point, it was really about making the hardware, the utilization be as high as possible for hardware. Now we want to make it as useful as possible for people, and so this is the rise of graphical user interfaces. Anyone know where the GUI was first developed? Xerox PARC. I heard Apple. No. Steve Jobs saw it at Apple and copied it. But he made it widespread and popular. Xerox, they failed to be able to commercialize the graphical user interface. Xerox developed a lot of the technologies that we take for granted today, like laser printers, mice, bitmap displays, networks, GUIs, and so on. Okay, so third phase, which is what we're in right now, is where hardware is really cheap. So you have smartphones that cost a few $100s. You have laptops that are a few $100s. And humans are really expensive. So anybody happen to know the starting salary for a Berkeley CS graduate in the Bay Area? Oh, I hear all over the place. Wow. So the numbers I heard are 80K, and some companies are offering 20K bonuses, signing bonuses. So the hardware is extremely cheap. The people are really expensive now. So really you want to optimize around the people and not around the computers. Because if I can make a person just a few % more effective by getting them a bigger display or a better computer, much better to do that, right? Because I'm going to make that money back very quickly on the output of that person. So devices now are ubiquitous. How many people have a smartphone? Okay. The trend on smartphones is exponential in terms of growth rates. As the cost of smartphones has dramatically dropped. Networking, of course, is ubiquitous also. So we have Wi-Fi here. You go outside, and we have 3G and 4G networks everywhere. Okay, so this rapid change in hardware has led to changes in the operating system, which have unfortunately lagged. So the latest generation, as an example of smartphone processors, include support for virtualization. It'll probably be a couple of years before we actually have smartphone OSs that take advantage of that. So we've gone from a batch model where you take your job, you submit it, and sometime later, could be a day, a week, some period, hours later, you get back an answer. You'll get to experience that in this class, actually, because we have the autograder, which right before the project is due can take many hours to return results. Submit early. Multi-programming, where we have multiple batch jobs running at the same time. Time sharing, where you're able to log into a computer that many other people also log into. Again, you'll experience that in this class. If you log into any of the instructional machines remotely, you'll see there are a lot of other people logged in also. the rise of the graphical user interface, and finally, ubiquitous devices where we have mobile operating systems. And what you'll also see is a gradual migration of features from the big machines to the smaller machines. And I'll go through that in more detail on the next slide. So interestingly enough, the situation today is much like the late 60s. A small operating system like, say, what runs in this projector is probably 10 to 100,000 lines worth of code. I'll bet that projector does Wi-Fi and it's networked and all these other great things. A large operating system could be tens of millions of lines of code. And the challenge here is that it takes a lot of people years, 100 to 1,000 people years, to develop new operating systems. If you look at the rate of deployment of new operating systems, say look at Windows or look at Mac or any of the others, what you see is a gradual slowing in terms of how quickly they're able to get new releases out. If you look at the 90s, every few years they were releasing a new operating system. 95 for Windows 98, 2000, 2003, and then it was like big gap between XP and Vista, and then a big gap between Vista and Windows 7. Okay, so here's a slide that tries to capture the migration of features from big computers to small computers. And what you can see is that there's a pretty significant gap, like an order of 10-year gap between when some feature appears in a big iron, say, and then when time sharing appears in mini computers or when desktop computers become multi-user. Okay? But the general trend is that features that appear up here end up eventually appearing in the smaller devices. Interestingly enough, there are some examples of where features have gone in the other direction. I'd say the biggest example of that would be multi-touch. So multi-touch actually appeared on the desktop first when you had tablets that supported multi-touch, but really there was almost no adoption at all. Multi-touch became popular in smartphones because the capacitive displays, it was easy to make them support multi-finger gestures. And now that is backward migrated into desktops through things like the mouse pads on MacBooks and the Mighty Mouse and so on. Okay, any questions? Yeah.
In terms of OS growth, what if you just look at the kernel of an OS? Have those really grown that much?
That's a really good question. So if you just look at OS kernels, have they grown a lot? Well, if you remember from last lecture, there's a question about what's in the kernel. And, is the browser part of the kernel? If you say yes, then you end up with an extra 5 million lines of code. But even if you do remove that, there's more functionality that's being added all the time. And so the answer is, yeah, there's a slow growth. Again, the question is, should that functionality be outside the kernel or inside the kernel? And different people will make different conclusions. Sometimes it's marketing based, sometimes it's truly functional. Yeah. So originally, handheld computers, the programming environment was assembler. Now, smartphones have as sophisticated development tools, things like Xcode, that's as sophisticated as what you see on the desktop or in other environments. But originally, handheld, single at a time kind of application. Okay, any other questions? All right, so what are we going to talk about today? We're going to talk about how to provide multi-programming. We're going to talk about processes and how processes are related to threads and to address spaces. Hopefully a lot of this is review because you've seen it before in the lower division, but we'll refresh and try to make sure we're all on the same page. Okay, so we start with threads. Threads are our unit of execution. It's an independent fetch, execute, and decode loop. And it's the unit of scheduling for an operating system. That's the smallest sort of thing that we can schedule is threads. And they operate within some address space, some memory region. Okay, so here's from 61C a picture that should look familiar. We have our address space here. It's a 32-bit machine, so we have 4 billion possible addresses broken up into there's some code and there's some data. We have our processor. Our processor has associated with it a register file of registers. It also has a program counter and some other registers. And it has an ALU, which is capable of an arithmetic logic unit, which is capable of fetching instructions, decoding those instructions, and executing. So what happens? We fetch the instruction at the program counter, we decode that instruction, we execute it using the registers if necessary, and then we write the results back to registers or to memory. Okay? And then we increment the program counter to be the next program counter, next instruction rather. And if it's an ordinary instruction, we're just simply incrementing it. If it's a branch, then it's some more complicated function that we're going to execute. And we repeat this. Okay? That's all a processor ever does. So our program counter increments. Okay, now let's talk about the difference between a uniprogram system and a multiprogram system. In a uniprogram system, we have a single thread that runs at any given time. Okay? And examples of this are Microsoft's disk operating system, early versions of the Mac, and batch processing. Okay? Only one thing is executing at a time. Now, this makes it much easier if I'm trying to build an operating system because I don't have to worry about concurrency because I've defined it away. All right? So there is no problem with concurrency because there is no concurrency allowed. A little bit of cyclic reasoning and simplicity. This is how original personal computers operated. Does this really make sense as a model for a PC? What's that? Yeah, evidently not. We added in. Why? You know, because I want to be able to listen to an MP3 while I'm working on the lecture notes. I want to be able to save the lecture notes in the background while I'm typing them. I want to be doing spell checking in the background while I'm typing them. I want to print a copy of them in the background while I'm typing. So, you know, we want to be able to do multiple things at the same time, and this is a model that was forcing you to do one thing at a time. Okay? Now again, when the hardware is really expensive, it does make sense to kind of optimize around the hardware and what the hardware is doing. But when the hardware is cheap, we want to optimize around the person and making them more efficient. So this is where multiprogramming comes in. In multiprogramming, we can run more than one thread at a given time. Right? And examples, first example really in the big example in the mainframe world was Multics. Unix and Linux OS/2 developed by Microsoft and IBM jointly. The versions of Windows, modern versions of Windows, and modern versions of the Mac all support multiple threads running at the same time. Some people call this multitasking, but multitasking has other meanings. We'll come back to this later on. Okay? All right. Now, the modern thing that people talk about a lot is many-core. And this is where I have not just one CPU core, but multiple CPU cores. And so I can run potentially many, many threads at the same time. So it's a form of multi-programming at the hardware level as opposed to trying to implement it at some software level. Okay? Kind of equivalent to if I have a multiprocessor also. Okay, now, what are some of the challenges of multi-programming? Well, each application is going to want to have its own machine. We can get this by using the virtual machine abstraction we talked about before, and we'll talk a little bit more in detail today about what it takes to implement that abstraction so we can give each application, its illusion of having the entire machine. We have to worry about the fact that we have a limited set of resources, and these applications are all going to be competing for those resources. So there are two roles for the operating system here. The first role is arbitrating access to those shared resources. So this is concurrency control. The second is protecting applications from each other. So we don't want a misbehaving application to cause problems for other applications running on that computer or for the underlying operating system. And so this is the protection role that the operating system is going to provide us with. Now, we could provide complete isolation, but that's not really useful. Because applications want to talk with each other for a variety of reasons. And so we actually also want the operating system to mediate that communication. So this is another concurrency control role that the operating system is going to take. And we'll see a couple of different ways that we can have communication between applications through the operating system. Okay, now processes take a thread and encapsulate one or more threads sharing a set of resources. So memory, an address space, and a set of file descriptors, file system context, I/O state, basically. All right? So two components to a process, a unit of resource allocation and these active threads that are executing within that process. Now, why do we use processes? Because they help us deal with this kind of fundamental trade-off between providing protection and having efficient operation. Right? Within a process, that memory is protected from other processes. Right? But within that process, the threads can all efficiently access the memory of the process. Right? So very efficient for communication. But those threads are sharing that address space, and if one thread misbehaves, it can bring down the entire process. Right? But that'll still be isolated from the other processes running on the system. So threads are more efficient. We'll talk about exactly why they're more efficient. But they don't have memory protection, which is a good thing if I want to do sharing. It's a bad thing if I'm worried about a thread misbehaving. So this is a trade-off you're going to have to make when you're writing applications of, do I run these applications as a single process with multiple threads, or as separate processes, or some combination of both? Right? An operation I don't trust, I might run that in a separate process. So if it fails or it tries to do something it's not supposed to, it's contained. But for efficiency, I might want to have them all run in the same address space. Yes?
Threads can be put on other cores or other CPUs or distributed just like the process could be, right?
Yeah, so the question is, a thread can be put on other CPU cores equally the same with a process. Yes. Although some operating systems do allow you to pin a particular thread to a particular core. And you might want to do that for caching reasons, so you get better caching performance. Okay, now an application will consist of one or more processes. Right. So the basic problem with concurrency is that we have limited resources. So we have a single CPU, single memory, and a single set of I/O devices. And we have this multi-programming API where processes think that they have exclusive access to all of these resources, the CPU, the memory, and the set of I/O devices. So the operating system has to coordinate all of this activity, the multiple processes, the I/O devices and their interrupts and things, and has to keep all of that straight and consistent. All right? If it delivers data from one interrupt to the wrong process, bad things will happen. So the basic idea is we're going to use this virtual machine abstraction. This is a simple machine abstraction that we provide to each of the processes, and it allows us to multiplex these abstract machines on the limited resources that we have. Okay, the single CPU, the single set of instances of I/O devices, and so on. Okay, now, Dijkstra used this very simple abstract model for his system, which he called the system, built back in the 1960s. He did it in a few thousand lines. At the same time that IBM had thousands of programmers working on OS 360, and by the time they delivered it after many years, I think it was almost a decade of development, it was delivered with 1,000 known bugs, known published bugs. Okay? He was able to do the same thing by coming up with this nice abstraction model in many fewer lines and in many fewer bugs, obviously. Okay, now, how do we actually make this illusion real? All right, so we have the model of we want to have, say, 3 CPUs representing 3 processes with a shared memory running on our single processor. So how do we provide the solution? Well, the simple way is to just simply multiplex in time. All right, so we're going to take that single processor and first run what CPU 1 would have done. Then we'll run what CPU 2 would have done. Then what CPU 3 would have done. And repeat. Run CPU 1, run CPU 2, run CPU 3, and so on. Ad infinitum until they finish. Okay? So what we're going to need is a virtual CPU that has a structure with program counter, stack pointer, and all of the registers. Right? Gee, this looks familiar. This is exactly what the real CPU has. Okay? So when we want to go from running CPU 1 to running CPU 2, we're going to do what's called a context switch. We're going to save all of the processor state. That's the stack pointer, the program counter, and all of the registers in a current state block. Then we'll load the state block for the next thing that we want to run. In this case, virtual CPU 2 will load its program counter, stack pointer, and all of the registers. All right. Now we'll talk about in later lectures It's a lot more complicated than this in terms of all of the different things you have to implement in order to do that. Now, what will make a switch from CPU 1 to CPU 2? Well, there's a few things. One is a timer could go off, say every 10 milliseconds, and when that timer goes off, we switch to the next thread. Okay? Another would be voluntarily yielding. Nothing more to do, transfer control to the next thread. Or if we perform some I/O. So if we go and we try to read a block from the disk, well, that's going to take time, and we don't want to just sit there holding the processor while we're not doing anything, and so we'll give up the processor and allow something else to run. Okay. Now, properties that we get with this very simple technique, all of this virtual CPUs share the same I/O devices. They share the same memory. Okay? And so the consequence of this is, as I said before, when we're operating within the same address space, we get the advantage of very efficient sharing. Right? The disadvantage is one thread misbehaves, it can scribble all over the contents of memory and disrupt things for the other threads, cause the process to crash. Threads share instructions. This is good for performance. We need less memory. We're running the same code. It's bad, again, in terms of protection. All right? We're actually operating within the same address region as the operating system, and so we can access all of the operating system's data structures. We can also scribble all over them. We can scribble all over the instructions of the operating system. So that's probably not very good. But this is actually the model that we find in embedded applications. All right, so that projector has multiple threads doing things, but they're all running within the same memory. Right? Now, what happens if one of those threads misbehaves and scribbles all over the operating system for the projector? Well, it'll probably get a blue screen or something like that, and I'll just power cycle the projector. Right? So there's really no need for protection between the threads, because if anything goes wrong, everything went wrong. Early versions of Windows, early Macintosh, were similar in terms of this unprotected model. So one misbehaving application could bring the entire system down. Also, you only switched when you yielded. So again, if you had an application that decided it wasn't going to yield, then you would not make forward progress on the other applications. It's a very cooperative kind of multi-programming model. Windows 95 and beyond added a switch with both yield and also had preemptive multi-programming. So you'd actually have a timer interrupt go off and force you to yield the processor. Okay. Now, I want to talk about a hardware-based approach to implementing concurrency called hyperthreading. And the basic idea is the following. If you look at a typical superscalar microprocessor, I have multiple function units. And if I look at a thread running on that processor, you can see that there are various gaps. Right? I'm not able to take advantage of all the ALUs on the processor. And I'm also going to have stalls. So this might be I'm stalled reading an instruction or stalled on writing some data or loading some data. So what the folks at the University of Washington recognized was if I looked at what multiple threads were doing, you can see that these threads have sort of gaps in them in their usage of the ALUs. And so I could actually run them all at once. Okay, so I'm interleaving at the hardware level. And all I really need to do this is, aside from some scheduling logic, is just duplicating the registers. Right? So if I want to run two threads simultaneously, I just simply duplicate the registers. Right? And given that Moore's law means we're getting ever-shrinking features and ever more devices that we can put on a chip, duplicating the registers is actually a very low-cost thing to do. Okay? And by doing that, I can now schedule each thread as if it were running on a separate CPU, and the hardware is going to take care of actually implementing that. Right? So it looks like I have two processors from a software standpoint, but in reality, I just have one processor that's hyper-threaded. Yes? So I have to have, for each, the question is, what do I mean by duplicating the registers? I have to have registers representing each of the threads. So I need the full set of registers, stack pointer, program counter, all the floating point registers, all the integer registers, the MMX registers have to be duplicated, one for each one of the threads. Okay? And then the hardware is going to take care of scheduling those threads onto the underlying physical resources, the ALUs, and so on. Yeah. This is implemented in hardware. So in fact, all modern processors support hyperthreading, or also called simultaneous multithreading. Yes?
Is it smart in that the hardware knows, like, knows it's pattern beforehand and then lines it up in this way, or is it just run things at once and hopefully they don't catch them?
Yes, that's a very good question. The question is, does the hardware know in advance what the instruction stream is going to look like, or does it have to just do it on the fly? The answer is it has to do it on the fly. So on the fly, it's looking at what is the available ALUs and what ALUs are needed by the next instruction that I've just decoded. And so as a result, what you'll notice here is here we have demand for 4 functional units, and we only have 3. So we end up having to delay one of the yellow's usage of functional units into the next slot, right? Which it actually fits in well because we have one vacant slot here, so we're able to fit all these 2 instructions actually run in 2 cycles, but this first instruction is actually delayed an extra cycle. Yeah.
But my question, I guess, is the fact that it delays the left-hand yellow spot down to the next step, that happens coincidence? Take this example, or does it know that it's going to be this next empty spot?
Okay, yeah, I understand what you're saying. So the question is the fact that the yellow gets delayed something that it knows it can do, or is it a happy coincidence that there's empty slots? It's actually an unhappy coincidence, right? The fact that I've got demand for 4 when I only have 3 is bad, and so that's why you'll get nonlinear speed up. And depending on what the demand is in the next slot, we might end up getting delayed further. So a lot of server software vendors will tell you if you want to get consistent performance, it's better to turn off hyperthreading than it is to use hyperthreading, because you're not guaranteed that you're going to get, it looks like you have 2 CPUs, but you're not going to get necessarily 2 CPUs worth of performance out of that server. Yeah. Average, good question. What is the average speed up? It's going to depend on the thread's demand for the various threads' demands for ALUs. Question in the back?
Kind of like with pipelining, can a compiler sort of set things up maybe to run a little better than those?
That's a good question. So could a compiler set things up better? Originally, you could have thought of this as trying to do this kind of scheduling in software of the ALUs. But now it's much more efficient to put it into hardware because you need to make the decisions quickly. An interesting question would be, could you divide up your threads such that they would use the ALUs in a more efficient manner? And the answer is yes.
And also, could threads have different caching?
No. Yeah. So the cache here there's a single cache, but you can tag it for each of the threads, yeah. Were you going to add something, Jan?
Yeah, so the question about the compiler. So this will also take advantage when you have different applications, which they are not produced by the same compiler, so different threads with different applications. If the compiler doesn't have a global view to generate the code, generate only for that.
Yeah, that's a very good point. Just to repeat for the podcast, the compiler has a localized view of a single application, whereas this operates at below the operating system, so it has a global view of all the threads that are running. So in fact, if you have hyperthreading on your computer, which most computers will have, you can look and see how many cores you actually have. And you might say have 2 cores. So for example, this has 2 cores that are hyperthreaded. So I'll actually see 4 CPUs if I look at the operating system's view of the world, even though I only have actually 2 physical cores that it can run on. Yeah?
So back to this example really quick. Between the 2 yellow boxes, or the 2 yellow boxes, it arbitrarily just chooses the first one to push down first.
That's correct. So it's making some decision based upon some logic as to which of the operations to delay for the yellow thread. Yes? Superscalar processors are processors that have many ALUs, many functional units. Any other questions? Yeah.
I noticed in the first column, the sixth row, the yellow
Which row?
like in the hyperthreading, the first column, the row, the yellow thing that they both overlap. Yeah, there's no difference.
Are you talking about down here?
Right.
It may have just pushed it below. Is that what you're saying? Yeah, I think it's just, oh, you're talking about this row? It's just rescheduling when the instructions actually get to run. Yeah, so this is again why you may not see linear speed up, is because at this point there's too much demand between what the yellow wants for resources and what the green wants for resources, and so it's just trying to fill slots as best it can. Again, you'll get a performance improvement, but it will not be consistent. If you have a server, you really care about consistent performance because you want to meet some service level objective. And so that's why you'll tend to turn off hyperthreading. Yes?
So with hyperthreading for a specific thread, you actually have to slow it, or is that?
That's correct. So for a specific thread, you could have slowdown with hyperthreading, depending on the demand on the ALUs and how the processor actually schedules the functional units. Okay, we should probably move on. All right, so how can we protect threads from each other? One approach is to use memory protection. That allows us to put them into different address spaces. They can't access the memory of another process. Another approach is to protect the I/O devices, so we can mediate access to the I/O devices through the operating system, so every thread does not have access to every I/O device. And then we can protect the processor. Okay, so we can mediate the switching from one task to another through the processor by using a timer. Okay, and making sure that the user thread can't turn off that timer. So we're going to force it to give up control if it doesn't give up control. Okay, now recall that an address space consists of all of the addressable locations associated with a process. All right, so for a 32-bit processor, this max value here will be 2 to the 32nd, or 4 billion possible addresses. And what's going to happen when we actually write to a location? Nothing might happen. So if we write to some unmapped region, nothing may happen. It could act like regular memory if we write to the heap or to data. Maybe if we try to write to a text location, it's read-only, so it's not going to allow us to do that write. Some regions may be actually mapped into I/O devices, so maybe writing to that location causes a pixel to change color on my screen, because it's mapped into my graphics buffer. Or it may cause an exception. So if we try to write off the end of the stack and it's not mapped, that might cause some kind of fault to occur. Now recall again from 61C that we have a physical address space here. We have virtual address spaces, and we have a translation map for each of those virtual address spaces that maps the various regions of those address spaces to physical regions. So we've mapped the code for virtual address space 1 to here. We've mapped the data to here, the heap to here, the stack to here. We've done the same thing for virtual address space 2. Right. Some important takeaways. There is no way from virtual address space 1 to access any of the physical regions associated with virtual address space 2. All right, so we've protected one address space from another. More importantly, there's no way from either of the virtual address spaces to access any of the operating system's code, data, heap stacks, or any other operating system specific locations. All right, so we protect processes from protect address spaces from each other. We protect address spaces from the OS or vice versa, the OS from the address spaces. Yes?
Where are these translation maps stored, and how does the operating system switch?
Very good question. Where do the translation maps get stored, and how does the operating system switch between them? We're going to have a lot of lectures where we talk about that process. It's not a simple thing. Sometimes it's stored in the processor. Sometimes it's stored as part of the OS's data. And then the switching process has to be done in a secure manner, because what would happen if, say, program 2 could change its translation map? Really bad things, right? Because it could make its translation map point at operating system specific data, or read or write the data of other programs. Yes?
Does the virtual address space start out as kind of a fixed theoretical size? Or maybe grow as they need to?
That's a good question. Does the virtual address space start out at some fixed size? Yeah. Typically, there is a limit on the size of a virtual address. For example, on a 64-bit machine, I could generate 2 to the 64-bit possible addresses rather. Obviously, we don't have machines that have 2 to the 64 bits worth of memory. So there is some mapping between the virtual address space and the much, much smaller physical address space. Typical maximums might be, you can put a couple hundred gigabytes worth of memory into a machine. Yeah.
Could one process essentially use up all the memory and then do kind of a denial of service on the
Very good question. Could one process use up all of the memory and physical memory and do a denial of service on others? That's mediated by the operating system, and again, we'll have lectures where we talk about how to deal with that and how to deal with the demand from multiple processes. Other questions? Okay. So some administrative stuff. We're using Piazza instead of the newsgroup. If you have not already signed up, you should sign up. It's really, really important, because that's how we're going to communicate all important things about this class to you. It's also the first place to go when you have a question. And when you have a question, please, as a first thing, search first in the current semester to see if someone has already asked the same question, and then search last fall, because someone may have asked the same question last fall. In fact, I've been talking with the Piazza folks, because we're going to try and see if we can't get search implemented so you see both the search results for the current semester and for previous semesters. Only 146 of you are enrolled when I last checked at the beginning of the class. We have way more than that in terms of students in the class, so make sure that you register. If you need an account form, you can either see one of the TAs after class, or you can email cs162@Quarry, and we'll give you account details. And Java, we're going to make extensive use of Java in the class. So if you don't know Java already, or you don't know it very well, I encourage you to very quickly take the self-paced course, CS9G, because you're really going to need it. And finally, lecture and section attendance is mandatory. It is 5% of your grade, and we may enforce that by taking attendance in section or having random pop quizzes in lecture. So please attend. We'll try to make these interesting enough that you want to attend. Okay, project sign up. If you haven't already, you need to, yeah, question? It's part of the 5% of participation. Project groups have to be 4 to 5 people. They cannot be 3 people. They cannot be 6 people. You cannot have 10 of your friends that you've worked with since high school in your project group. 4 or 5. Break into 2 separate groups. You all have to attend the same section. Okay, it can't be the same TA. Has to be the same section for the entire section time. Can't be half of the section or whatever. It's really important that your TA be able to communicate with you in one place at one time. And so that's why we require you to be in the same section at the same time. Submissions for project groups are due by tonight at midnight. If you have not found project partners, there are a lot of people looking on Piazza for additional partners. We don't like to have to do matchmaking, but if there are people who can't find groups, we will find them groups. But our first choice is that you organically find people to work with. Yeah? No, you don't need to re-register. It's just really important that, so the question was, do you have to log into your account before you click on that link? The true answer is no, but when we run the scripts to do the assignment, it's going to pull from the gradebook and give us a list of names. If you haven't registered, we won't be able to pull your name, and that causes all sorts of problems for our scripts. So that's why we need you to register before midnight so that when we click on that button, when we actually do the assign operation, we'll get the right values. Yeah?
Fault tolerance for the group, if somebody drops or if two people out of 5 drop.
So the question is around fault tolerance for our groups. Drop date is Friday, so hopefully people who are going to drop are dropping right now. If we have to, we will rebalance if we end up with a group of 2 after Friday. But hopefully we won't have to do that. Yes? So we're going to post that at the group and section assignments link that'll appear on the left bar, so make sure you refresh your browser to see that bar. We'll make a post on Piazza when we do that. We're going to run the script after midnight, and there's a little bit of manual work that we need to do because we're going to try and give everybody their first choice, and we need to balance the workloads across the sections and across the TAs. So there's a little bit of manual work that we have to do after we've gotten everybody's preferences. But we'll post on Piazza as soon as we've actually done that. Yes?
I believe that the drop deadline has to be
That may be correct, but I think you have to petition for certain classes, and I think, yeah, I think we're an early drop course. Yeah. So if you're thinking about dropping, drop now. Don't drop. Stay in the class. It'll be a fun class. A lot of work, but it'll be a fun class. Just to refresh, these are the section times that we have, and in particular, these sections we're looking for a lot of people, so make sure you list those. Any questions about the section assignment process? Okay, so projects. The first 2 projects are definitely going to be based on nachos. We haven't decided about the latter 2. They will be identical to the prior versions of 162 projects in nachos. And so as a result, I strongly encourage you to read the walkthrough that Dan Hetna wrote. It's really short. And then start reading the code. It's really long. I think double column, small font. It's about 169 pages. You don't need to read all of the code, which is why I said read the walkthrough first and then start reading the code. It's a daunting amount of code. This is probably going to be the largest code base that you're given to start with and have to modify in many places. So I strongly encourage you to start thinking about it. This is why I said Java understanding is going to be important. It's a lot of Java code. Also, using a good IDE like Eclipse is going to be really helpful for finding all the little instances where you have to change a particular variable. Questions? Yeah.
How do we set up the collaboration environment?
Excellent question. How do you set up the collaboration environments? There are lots of pointers on the Nachos page. We have an Eclipse walkthrough that uses CVS, so ignore the CVS part of it. There is a how to use SVN with this class walkthrough. There's also one done by Instructional that talks about how to use SVN or PRCS or Git or some other source code control system. We'll set up the accounts for you, the shared repositories, and then it's up to you to decide how you want to access and manage them. Any other questions? Okay, so the second 2 projects are going to be more complementary. They will be more systems oriented, although with strong OS components. The third project is going to be a single server key value store, so puts and gets, an in-memory hash table that you'll have to implement, and it's going to be on Amazon EC2. So how many people have used Amazon EC2 before? Excellent. So you're going to get really a good experience using EC2. And project 4 is going to be a distributed version of that. So multiple EC2 machines that you'll be using to implement a distributed hash table with replication using 2-phase commit. We're also going to add in encryption for both the data and the communication between instances. Questions? Okay, with that, we will take probably more like a 3-minute break so we can catch up. Okay, let's get started again. All right, so quiet down so we can get started. So let's talk about the traditional model for a process. And this we'll call the traditional Unix process. And the definition of a process is it's the operating system abstraction that represents what is needed to run a single program. Okay, that's the original Unix definition. This is often called a heavyweight process, and you only have a single sequential stream of execution within its own address space. Okay? Basically, that means one thread in one address space equals a process. Right? So there's two parts to this. There is the active part, which is the thread, the sequential program execution stream, And that includes your CPU registers, your I/O state, everything else. And then there's a set of, and along with that is a set of protected resources, rather, which is your I/O state and your main memory state. All right, so there's the execution stream, the active part, and the passive part, which is the memory and the I/O. All right? There's no concurrency within a heavyweight process. So we can have multiple of these running on a system, but if you crack open a heavyweight process, there's only one thing going on at a time. All right? Now, how do we actually multiplex the processes? Well, we're going to do that using, just as we had a thread control block, now we're going to have a process control block. And in the process control block, it represents a snapshot of our execution and protection environment. So it has all of the process state, not the memory, just various things about what's the process doing, the process ID or number, the program counter, the registers, the stack pointer, and all of that, any memory map information, and then the I/O stuff, so the list of open files, okay, and anything else that we need. Only one process control block will be active at a time in our system, so only one thing is running. And we give out CPU time to different processes through the scheduling operation. Right? So this is where we choose which process is going to run and then run that process. Right? Processes that have higher priority, we'll give more time to them. Lower priority, we give less time to them. We're going to talk about we're going to have a whole lecture on CPU scheduling and all the different choices that one can make and all the different algorithms one can implement. All right, now, the second part of this is protection, where we want to control access to non-CPU resources. So two examples are memory mapping. We'll give each process its own address space and make it so that one process can't access the memory of another process. And then through this controlled access to the kernel, right, or controlled access to the operating system. And this is what we'll use to control access to I/O devices. Right, so when we're within the operating system, we can access all of memory, all the I/O devices. When we're in user space, we can't access any memory other than that which is assigned to us, and any access to I/O devices gets mediated through system calls into the kernel. Again, we're going to spend a lot of time talking about exactly how we implement that, given that we only have one physical processor and we're trying to multiplex multiple operations on top of it. Okay, now, how do we actually switch from running one process to another process? This is a figure drawn from the book. We have process 0 here, and we want to switch from executing process 0 to executing process 1. Right. So something will occur, like a timer interrupt, or process 0 might do a system call because it wants to access some I/O device or some other operation. That'll cause us to go into the operating system. Ignore the details of how we do that for now. We'll talk about it in a later lecture. But the first thing that the kernel is going to do is it's going to save the state into its process control buffer, or block rather, for process 0. Okay? It'll do some other bookkeeping, housekeeping, and other things, select which process it's going to run next. In this case, it picks process 1. It reloads the state from process 1. And then we switch from the operating system atomically into running process 1. Lots of details I skipped over. We'll go through those later on in the semester. Now process 1 executes. Eventually either an interrupt or a system call occurs back into the kernel, save the state into the process control block for process 1, do some bookkeeping, reload the state for process 0 from process control block 0, and then switch back to process 0. Okay? This whole operation of going from process 0 to process 1 is a context switch. So there's two context switches that occur here. One from process 0 to process 1, and then one from process 1 back to process 0. Yes?
So is an interrupt anything from like a mouse click to point in some device, or
All of the above. So an interrupt could be generated by a hardware event, like something has been plugged in, or I unplug the power from my laptop, or I click on a key or on the mouse, or a byte comes in from the network, or a block comes in from the disk. Or it can also be a software. There are software interrupts that can also occur. So, yes?
are you switching in between internal context or whatever
you can either define this as going into the kernel as a context switch into the kernel and switching out as another context switch, or most people usually just think of it as a context switch from includes the switch into and out of the kernel. So for example, where it might be different is if I do a system call, and that requires switching into the kernel and then switching back out. So the time it takes us to do this switch from one process to another process is overhead. It's wasted time. We're not doing anything useful when we're switching, if we're switching, for example, because of an interrupt, like a timer interrupt, from one thread, one process to another process. That's just extra overhead. So for example, if it takes us 2 milliseconds to do this switch from process 0 to process 1, and our timer is 10 milliseconds, that's a 20% overhead on operation. 20% of the time, we're not actually doing useful work. Right? So in that case, we'd probably want to set the timer to be much, much higher, like say 100 milliseconds, in which case then we'd only be spending 2% of our time instead of 20%. Okay? Or, alternatively, we'll try and make this context switch as efficient as possible and as quick as possible. Okay? Yes?
Where is the timer set? I mean, dynamically determined?
Very good question. Where does the timer get set? Usually it's fixed, and it's done by the operating system developer. So they'll say, we're going to have a time, and it might be 13 milliseconds, it might be 20 milliseconds. It may also be a function of if this is a real-time system, I'm going to want a timer that's much shorter so that I can react to things quicker. It depends. But usually, it's not usually dynamic. There was a question in the back, yeah.
What gives the OS its magical blessing to have full control? Is it like there must be some hardware enforcement of that?
Absolutely, yeah.
Like memory that
Yeah.
is sitting in?
So this is skipping way ahead, but there is hardware support for implementing this kernel user mode duality. So there are things you can do when you're in kernel mode that you can't do when you're in user mode, and that's enforced by the hardware. And the processor actually has special hardware to allow you to securely get into kernel mode and allows you to then control the dropping of that permissions when you get out of the kernel mode and go back into user mode. So an alternative is when we have multiple threads and we're letting the hardware do the switching between those threads, so which we saw in hyperthreading. The downside, though, is that we have contention for resources that's not controlled by the operating system. All right. Okay, any other questions? Okay, so let's look at the life cycle of a process. So as a process executes, it's going to go through these different states of operation. First, the process is created in the new state. Then it's admitted to the system and put on a ready queue and marked as being ready. That means it's ready to run. And then eventually, the scheduler picks it and it gets to run. Okay? And it'll run for some period of time until something occurs. All right? It could generate an I/O request or wait on another process, in which case it'll be put into the waiting state. When that event completes, like that I/O or that process, it'll then be put back into the ready state and be ready to run again. Okay? An interrupt will also take you back to the ready state, right? Because we'll take the processor away from you and give it to somebody else. And then finally, it leaves the running state and exits, and it's terminated. Okay? And we actually have a separate state because we have to do some cleanup after a thread exits. All right? Okay, now, the decisions about which order, so here's a picture that shows you, again from the book, shows you the various queues, and the decision about how you pull things from the queue is these scheduling decisions that we're going to make. All right, so in particular, how you pull things from the ready queue is completely a function of the scheduling discipline that you choose for the processor. But when you perform an I/O, you'll get put on the I/O queue waiting for that I/O event. If you create fork a child, that child will execute, you wait on that child, and then you'll get scheduled again. If you do something that causes you to wait for, say, some I/O interrupt to occur, then you'll wait until that interrupt occurs, and then again you'll get put back on the ready queue. Okay? Lots and lots of algorithms for managing all of this that we'll talk about when we talk about CPU scheduling. Okay, now how do we create a process? A couple of things that we need. We need a process control block. Really inexpensive. That's just a little bit of kernel buffer memory that we have to allocate in order to allocate a PCB. We have to set up the page tables for that address space or the segment registers or whatever. It's a little bit more expensive, but typically not very, very expensive. Now, the semantics of creating a process are typically that you do that by doing a Unix fork. And the Unix fork semantics are that you clone the entire memory address space for the child. Right. Now, 2 to the 32nd bytes in our address space. That copy operation was originally extremely expensive. What we do instead is copy on write. So what we do is we take and we copy just that translation map, and we mark all of the entries in the translation map read-only. Right. Now, if you ever try to write to a particular location, either in the child or the parent, that's going to cause us to trap, because we're going to say, hey, you're trying to write to some location that's read-only. And then we're going to look at a second set of books, which is the original translation map, and see, is that location really read-only, in which case we'll fault the program. If it's not, then what we'll do is we'll just copy that region of memory for both the parent and the child. Okay, that's called copy on write. So we're only ever going to copy when we actually write to a location. So this now makes the copying operation effectively instantaneous, because when we set up the new page tables, we're just simply going to clone them from the parent. Okay, did everyone follow that? We're going to go through this in more detail later on, but okay. And then the last thing is copying the I/O state, and that's medium expense. It depends on how much I/O state descriptors we have to copy. Yes. That's a good question. Are all processes created with fork? In a Unix system, yes, except for the initial process that gets created. All processes are created by our children of that initial process. So for example, on a Mac, if you look, you'll see everybody's a child of a given root process. Yes? No, the first process is created by the OS when you boot up. I think it's initd that creates the first process. Or initd is the first process that then creates everything else. Any other questions? Okay, so now we can ask the question, we've talked about processes, we've talked about programs, are they equivalent? Okay, so here I have a program on the left, and here I have a process on the right. Okay. Well, we can see that there are obviously some differences. So there's more to a process than just a program, right? Because a process includes data, it includes like a heap, it includes a stack and a set of registers and so on. You know, we can both run Emacs. You run it on project.java, and I run it on lecture2.txt, and same program, yet very different state. Okay, and very different things are happening. But then there's less to a process than there is to a program, because a program can invoke multiple processes. So for example, the C compiler, when you type GCC, first thing it does is invoke the C preprocessor. Then it invokes the first pass C compiler, then the second pass C compiler, then the assembler, and then the loader. Okay. Each of those is separate processes that's being invoked by one program. All right. Okay, now multiple processes can actually coordinate and collaborate on a task. There's a high creation and memory overhead associated with having a process, and it's relatively high context switch to switch between process 1 and process 2. So we want some kind of communication mechanisms that allow us to do this a little bit more efficiently. And there are two mechanisms that we can use. One is having, so we have separate address spaces. We can do shared memory mapping. So we're going to take in our translation map and make two regions of two separate processes point to the same location in physical memory. All right. And then we can just read and write through the memory for communication. The other alternative is message passing. So we'll have send and receive messages, which are basically going to be system calls into the operating system. And then the operating system will pass that message on to the appropriate process. Right? So the operating system mediates that communication. Right? This communication is unmediated by the operating system. The advantage of message passing is that it works across the network. It doesn't matter whether I'm sending a message to a process on my machine or I'm sending a message to a process on a machine on the other side of the globe. Right? It's transparent whether it's local or remote. The only visible from a user standpoint is latency. Because obviously it takes a lot more time to send something to the other side of the globe than it does to talk to a process on the same machine. All right, so here's an example of how we can do shared memory. We simply modify the translation map so that we have a region of memory which is visible in both virtual address spaces, which is represented by the same physical region in memory. Right, so any writes that are done to this location appear here and appear here also. So very low overhead for communication, but as we're going to see in later lectures, tremendous synchronization problems that get introduced. Right? Because what happens if both programs try to write the same physical memory location at the same time? Which value gets written? Okay. And what if that's my bank balance? All right, IPC as an alternative, interprocess communication, the send and receive, is a mechanism that gives us two capabilities. One is communication, and the second is synchronization. We can actually do synchronization through sends and receives. It's a nice way of communicating without having to have shared variables or shared memory region. We have two operations, a send of a message. Some operating systems fix the size of the message. Others allow it to be variable. And then a receive operation, which allows you to receive a message into a buffer. Okay, and there are blocking and non-blocking versions of these, synchronous or asynchronous versions of these. We'll go through a lot more detail of these when we talk about synchronization. Now, if two processes want to communicate with each other, they set up a communication link through the kernel, and then they just exchange messages using sends and receives. Okay? That channel can be unidirectional or it can be bidirectional, or we can set up two unidirectional channels in order to get a bidirectional channel out of it. Right? Different operating systems offer different sets of primitives. It can be implemented a lot of different ways. Some systems for efficiency will implement it in shared memory. Others implement it through hardware locking of a hardware bus. Others implement it through syscalls and traps. It can be implemented in a physical manner that's very visible, or it can be done very logically, so it just looks like you're reading and writing a byte stream. Okay, questions? Yes?
Can you give some examples of real life memory sharing between processes?
Sharing between an X client and an X server occurs using shared memory for efficiency, so you can transfer over bitmap images very quickly. So the X server is managing your graphics display. The X client is an application that is like an X terminal or Emacs window that wants to talk to the X server to put up a window. So they'll typically do that through shared memory if they're operating on the same machine. Yeah. Question? Yeah, it's implemented as an efficient, so the question is how is it network transparent if it's done using shared memory? The X client and X server are smart enough to realize if they're on the same machine, I can use shared memory. If they're on separate machines, then they'll use IPC to communicate. And that's actually all hidden away in the X library, so you don't actually even have to worry about it if you're writing X applications. Other questions? Yes? That's skipping way far ahead. So the question is, what ports do we use when we're using IPC? Depends on the system. So, for example, if you are sending and receiving messages between a web browser and a web server, the web server typically listens on port 80. But if you're sending between two applications, some systems like Windows systems have an RPC server. You talk to the RPC server to find out what port is this particular process listening on. But very system dependent. Other questions? Okay. All right, so we've talked up to now, we've talked about heavyweight processes, single thing going on at one time, single thread in that process. Let's talk about lightweight processes. And these are modern processes. So all modern operating systems provide lightweight processes. So we have threads. This is our sequential execution stream within a process. It's sometimes itself called a lightweight process. And a process still is a single address space, but now it's multiple threads, okay, with no protection between those threads. So all those threads are running within the same address space. This is called multi-threading, a single program made up of a number of different concurrent activities. The Ada language calls this multitasking, but again, we're not going to refer to it as multitasking. We'll refer to it as multi-threading to avoid confusion. And you could ask the question, why do we separate out the notion of a thread, this sequential execution stream, from that of a process? And it's because now we can talk about the two components of a process separately. We have the active part of the process, which is the thread, which we have to worry about with concurrency control. And we have the protection part of a process, which is the address space. And that's the passive part of a process. All right? And a heavyweight process, for backward compatibility, is just simply a process with only one thread in it. Okay, so we can take a modern Unix system and run an old Unix program where we only have a single thread. Okay? All right, so looking at the difference between single and multi-threaded processes, on the left here we have our single-threaded process. We have our single thread. We have registers, stack associated with that thread. And then we have our code, data, and files, and heap, and stack, and so on. Okay? On the right here, we have a multi-threaded process, multiple threads. We have the same code, data, and files as we did with the heavyweight process, but now we need to have separate registers and stacks for each of the threads. Okay? Why do we need to have separate registers and stacks? Because we need to represent the thread local state of each thread. All right? And then everything else within the address space is shared. Now, why do we want to have multiple threads within an address space? I just spent half of this lecture talking about how great it was putting different processes. You get isolation, one process crashes, it prevents you from crashing other processes or scribbling on the OS. So why would I now, after all of that, want to say a better idea is just put it all in one big bucket and allow them to duke it out? Yes? Exactly. We want the benefits of concurrency without the overhead of the passive part of the process, the protection control. All right? So we're not going to have to go through the kernel for these two threads to communicate. They can just simply communicate through the heap. All right? They don't have to do anything. There's no context switch into the kernel associated with having to communicate between those two threads. All right? So it's going to be much more efficient as a communication model. All right, so examples of multi-threaded programs, elevators in embedded systems, single program, multiple concurrent operations that are going on. Most modern OS kernels are concurrent with multiple threads operating within the kernel's space because you don't really need protection within the kernel. If something goes wrong, you're going to have to reboot anyway. And so it's sort of, you have shared fate, so if one thread screws up, it's going to be a kernel panic and the world's going to stop anyway. Database and other kinds of servers also are multi-threaded because you have shared data being accessed by many concurrent users and also some background tasks that have to be done, indexing and other things. Similarly, network servers like file servers and web servers, shared content, many concurrent users, and so a multi-threaded model makes a lot of sense. Parallel programming also makes a lot of sense to have multi-threaded because you've got multiple CPUs that you're trying to schedule activities onto. Sometimes this is actually done in a uni-programmed model. So you have one program that runs on like old HPC high-performance computing style machines. You had multiple processors all basically operating on the same program, on the same data. Okay. Thread state. So what thread state do we have? We have shared state in the form of the process and the address space, the contents of memory, the I/O states all shared. And then we have private state. We have state kept in our thread control block, like the registers and the stack. All right? The execution stack is where we store all of our local variables when we're doing recursion, our return program counters, and so on. So let's look at an example of the execution stack. So here we have a program consisting of 3 procedures, A, B, and C, and a main. Our main just consists of a procedure call to A. And our stack is where we're going to put our temporary results. It's a primitive we use to implement recursion, and it's a crucial component of any modern language is having a stack. Okay, so here's our stack when we've executed the procedure call to A with the value 1. The stack is now going to consist of temp equal to 1, so the local variable temp is set to 1. And our return program counter is going to be set to exit, because there's nothing after that call to A. All right. And our stack pointer points to the bottom of the stack. In this case, our stack is growing down. All right, so temp is equal to 1, which is less than 2, so we're going to call B. So what are we going to do? We're going to recurse into B, create a new stack frame for the call into B. Our return program counter is going to be set equal to A plus 2, so that's going to put us right here. And we move our stack pointer down. Okay? Call C. C is going to cause us to create a new stack frame for C. Return program counter is going to be set to B plus 1, so right here. Okay? And then C calls A equal to 2. All right, so now we recurse, call back to A equal to 2. Temp is now equal to 2. Right, so we're now in A twice. Right? First time we're in A, temp was set to 1. Now temp is set to 2. These are 2 different memory locations representing 2 different calls into A. All right. So this does not change, for example, the value of that to be 2. All right, so return is set to C plus 1, so right there. And what's going to happen? Well, temp is greater than 2, or is equal to 2, which is not less than 2. So we're going to print the value of temp. So we'll print 2. Then what will we do? We're going to finish, which means returning to C plus 1, which is going to finish, which is going to return to B plus 1, which is going to finish, which is going to return to A plus 2, which is going to print out the value of temp, which is 1. Okay? And we're done. Okay? Then we'll return to exit, which means the program ends. Okay. Any questions? Okay. So, quickly, let's go through classification. We can classify operating systems by one or many address spaces, by one or many threads per address space, and original versions of PC operating systems fell into the 1 and 1 category. Embedded systems, we have, in real-time systems, we have one process, or one address space, many threads. Traditional Unix was many processes, one thread per process, heavyweight process. And modern operating systems, many threads, many address spaces. Okay? I'll skip this and go to summary. So processes have 2 parts. There is a concurrency component, which is the threads, a protection component, which is the address space. Concurrency is accomplished by multiplexing the CPU in time. We do a context switch by unloading the current state of the CPU, loading the new state. And this context switch can occur either voluntarily through yields or system calls, or involuntarily through I/O or interrupt operations. Protection can be accomplished by restricting access to memory and by using dual mode operation to restrict access to I/O and other resources. And when the book talks about processes, when they talk about concurrency, they're talking about the thread portion. When they talk about protection, They're talking about the address space portion of a process. Any questions? All right, I'll see you on Wednesday.